Good morning, everybody. Welcome to Hydraulics and Hydraulic Machines class. Today, our discussion point is the working proportions of Francis turbine, which leads to the design of Francis turbine runner. So, before this, we have completed the components of Francis turbine. Once we completed the components of the Francis turbine, then we have taken up the velocity triangles, work done, and efficiency in case of Francis turbine. So after taking these two, the next will be how really the design of the runner can be done. And this leads to the problems in Francis turbine. So let us go straight away into the first is working proportions. Working proportions gives us only a relation between the parameters. That means, for example, what is the relation between the width of the runner to the what you call it as the diameter of the runner? What is the, for example, that equation for the tangential velocity? What is the equation for velocity of flow? Is there anything like that these things are what we call it as the working proportions? Once working proportions are known, then how to proceed with the design of the runner and approximately how the dimensions are fixed, approximately how many number of vanes are there. All these things will come one after the other. So let us straight away go into that. So the topic is working proportions of Francis turbine. I already mentioned what are the working proportions in the case of Francis turbine. Number one is what is the ratio of the width of the runner. The width is always noted by B, width of the runner to the diameter of the runner. Then this ratio we call it as N, and that N is equal to B by D, and it approximately varies between zero point 0.1 to 0.45. This is the approximate variation of N. This is the first point. Whereas the second point is what is the flow ratio? This already we discussed previously also. Flow ratio means actually what is the flow ratio? How we defined it? It is the velocity of flow at inlet to the theoretical velocity of jet. Theoretical velocity of jet at inlet, right? This is what we call it as flow ratio, and it is represented by Kf, and we call it as Vf, and theoretical velocity is always root 2 GH. So therefore Vf is equal to Kf into root 2 GH. This is the relation between the theoretical velocity and velocity of flow, and this Kf value varies from 0.15 to 0.30. This is the second thing. And what is the third proportion is what is the speed ratio? Speed ratio is equal to basically it is the peripheral velocity at inlet to what I call it as theoretical velocity of runner. That is equal to, it is what we call it as U divided by root 2 GH, and this is called as KU actually. So therefore U is equal to KU into root 2 GH, and the approximate value of KU varies from 0.60 to 0.9. So these are all called as the working proportions. Knowing these working proportions, we enter into the design of the Francis turbine runner. What do you mean by the design of the Francis turbine runner? Actually, it is basic. Normally, we have to design the runner to develop a known power. This is the first thing. When the turbine is running at a known speed, that is the second, under a known head. So the design of runner is to develop basically a known power. We have to develop it for a known power. And what is a known speed also. And at the same time, whatever the available head is also known. So these three parameters are known actually. And what we need to find out basically, what is to be determined? What is to be determined? What is to be determined? What is to be determined actually? What is its size? The size of the runner, that is number one. And second one is vane angles. This is the things that we need to design actually. So that is what the question is. How to carry out? The design is carry out. The design is carried out as follows. Stepwise. Number one, what is the first step? First thing is some assumptions we need to make. Assume suitable values for what? Overall efficiency, that is number one. Hydraulic efficiency, number two. Number three is what is the ratio of P by D, that is number three. And number four is this flow ratio. Number five is speed ratio. Overall efficiency, hydraulic efficiency, ratio of width to diameter of runner, and flow ratio, K. These are the things that which we know first. When once we know first, that means assume reasonably. For example, overall efficiency some 80%, the hydraulic efficiency 90%, B by D ratio that is zero point 0.4, then Kf is equal to zero point 0.3 and Ku is equal to zero point 0.8. So like that, these values have to be assumed suitably. That means depending on the conditions we need to take it, or otherwise for your purpose, for learning purpose, in the examination purpose, naturally these values also will be known to you. They give these values and some more data and ask whatever we put at the beginning. They may ask you to develop to find out the vane angles, or they may ask you to determine what you call it as the diameter of the runner, the width of the runner. They may ask you to find out, even sometimes giving them, ask you to do the power calculations. So how to proceed with the first, what we need to do is calculate. Your first step should be to calculate the discharge. This is the first thing. Please remember, in any of the turbine problems, especially the reaction turbines, the discharge, if somebody asked, means the equation that which we look for is overall efficiency is equal to the power shaft horsepower by water horsepower gamma QH. This is the equation which you need to look at always. right? And with this equation only, you can really solve the problem. Therefore, P is equal to overall efficiency into gamma QH. This is the thing. So now what is the question actually for us? P is known, and similarly gamma is equal to 9810, you know it. H is known and eta 0 is assumed. So therefore Q is equal to, how to get it? P by eta 0 into gamma into H. So use this equation to determine the power in any of the reaction turbines. Once discharge is has determined, so discharge is obtained. Once discharge is obtained, then your thing should be how to calculate the velocity of flow. This is the next step. How to calculate the velocity of flow? We know discharge is equal to area of flow into velocity of flow. So if that is the case, what is area of flow? Area of flow is equal to, generally, it is pi d1. This is the perimeter into the width of the runner. So to that extent, then, but this is theoretical. But problem is the vanes also occupy some portion. It is not completely a open, basically what you call it as a wheel, but the vanes are fixed. So if I account for the thickness of the vanes, then this thickness of the vanes leads to this much. So because of the thickness of the veins, overall area of flow reduces. So therefore, this KT1 will be always less than 1. Right? If suppose they don't give the thickness of the foam, the vein in the case of problems, then we normally assume that it is 1. Sometimes they will give, but approximately how much it will be? It will be 0.95. That means almost some 5% of the total area may be occupied by the veins. 5%, 6%. So 5%, 6% means if 5% is occupied, what is the remaining part? 95%. So that's why KT1 value should be 0.95. Suppose if it is 6%, naturally what is the KT1 value? It should be 100 minus 6, that is 94. That means 0.94. So this KT1 value depends on the percentage of area occupied by the veins. If that you reduce it, you subtract it, the remaining area is the area of flow. So now this is the thing. Again, our problem is here D1 is unknown, B1 is unknown. So what I do, I use the relation N is equal to B1 by D1. This relation I will use. Therefore, B1 is equal to N into D1. If you substitute in that, the area of flow is equal to KT1, this is number 1. Then pi, okay. D1 is okay. Instead of B1, you write ND1. Therefore, KT1 into N into D1 square. This is the area of the flow. So now we will get it. Q is equal to area of flow KT1 into n into d1 square into basically velocity of flow. So this is what. Therefore, what is velocity of flow? It is q divided by kt1 into n into d1 square. So this is the next thing. So now again problem is Vf is unknown, D1 is also unknown. So next what I am going to do. So we also know that actually we also know that Vf is equal to, what is Vf? Kf into root 2 GH. So if I substitute that Kf into root 2 GH is equal to Q divided by KT1 into N into D1 square. So Q is known, Kf is known, H is known, Kt1 is known, N is known. Only unknown is d1. So write the equation for d1. So d1 is equal to, right? d1 square is equal to q divided by kt1 into n into kf into root 2 gh. And if you want d1 is equal to q by kt1 into n into kf into root 2 gh whole to the power of half. That's all. So by using this, you can get basically the diameter. So the second step is also over. Now go to the next step actually. Next step is what? That is what we call it as the tangential velocity of wheel. Tangential velocity of wheel. What is the tangential velocity of wheel? That is what we write it as u. We know u is equal to pi d1 into n by 60. So using this equation, we can d1 is already determined, right? N is known. So u you can calculate. So u can be calculated. Then next, if I am moving, my idea already I told, when once basically diameter is known, then b by d is also known, b is known. So the size of the runner is over. Now I am moving towards the vane angles. When I am moving towards the vane angles, then the first thing I use is hydraulic efficiency equation. The hydraulic efficiency equation is VW1 U1 by GH for Francis turbine, because the discharge is radial at the outlet, thereby the VW2 is equal to 0. So this is for Francis turbine. So kindly see that in this eta H is known, U1 is known, H is known, G is anyhow known. So what is to be calculated? VW1 is equal to, how to get VW1? Eta H into G into H divided by VU1. So put this and get calculate VW1. So this is also over. Once this is over, then go to the inlet velocity triangle. Inlet velocity triangle. If I draw the inlet velocity triangle, what is the inlet velocity triangle? This is V1, this is U1, and if I join it, it is VR1. Then if I take the components of V1 in XY directions, this is VW1, this is VF1, and this angle is theta, this angle is alpha. So what is tan alpha for you? It is VF1 by VW1. So both are known, then find basically alpha. This is first. Then if you find what is tan theta is equal to, it is Vf1 divided by Vw1 minus u1. So knowing all the things, find basically theta. So alpha and theta both are over. This is over. Then what is the only thing remaining? The outlet velocity triangle phi is remaining. For phi, actually, it is at the outlet. So let us connect. What is the link between the inlet and outlet? The linkage between inlet and outlet. This we will try, because at the inlet we have done everything. So when we go to the outlet portion, first thing is assume the diameter of runner at outlet is equal to half of the diameter of runner at inlet. If you see the figures also, always the outer diameter will be of larger size, inner diameter will be of lower size. That's why generally the relation between these two will be this. This is the first thing. When once you assume this, what will happen? U2 also will be, because U1 and U2 depends on U1 is equal to pi D1 into n by 60, U2 is equal to pi D2 into n by 60. So therefore, U2 is equal to U1 by 2. Once this is done, automatically this is done. That is the next. Then basically, what is next? Next, the velocity of flow at outlet. How to find out? Velocity of flow at is equal to KT1 into pi D1 into B1, right? Into VF1. This is inlet. It is equal to KT2 basically into pi D2 into B2 into VF2. So generally what is happening actually, KT1, KT2 generally same. KT1 is equal to KT2 because the thickness may not vary from inlet to the outlet. Again, VF1 should be equal to VF2, right? That is number two. And therefore, what is the relation between because we already know D2 is equal to, already D2 is equal to half of D1. Therefore, B2 must be equal to twice B1, right? This is the next. So this is done from only this equation. So if you see in this, if D2 is equal to half D1, naturally B1 is equal to B2 by 2, or B2 is equal to 2B1. So knowing this, let us go into the last point of this. The last point is, what is the last point of it? Is the eighth one is, what is the runner vane angle? Runner vane angle. Runner vane angle phi at outlet. So for that, we draw the outlet velocity triangle. Outlet velocity triangle is this is VR1, and for Francis turbine, beta is equal to 90 degrees, VW2 is equal to 0, and this is V2 is equal to VF2, and this is U2. This is and this angle is phi. This is the outlet velocity thing. So therefore, tan phi is equal to, what is tan phi? VF2 divided by U2. So naturally, knowing these two, calculate phi. So this is over. So, but there are some parameters which we should also note. What are those parameters? Generally, the number of veins varies between 16 to 24. This is the first thing. Last point is, if there is no loss of energy, when water flows through the veins, H minus V2 squared by 2G is equal to 1 by G into VW1 U1 in the case of Francis turbine. Why I am writing Francis turbine? Automatically VW2 is equal to 0. So this completes to me the entire theoretical part of the Francis turbine. And in the next class, we will take up some of the problems in Francis turbine. So I will stop my lecture at this point, and let me take up some problems in the next topic. So that we will do some more problems in the Francis turbine in the next class. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.